All right, so let's go with the Maxwell-Boltzmann distribution. That's the velocity distribution when you are in thermal equilibrium. So the Maxwell, let me just write it out here, Boltzmann distribution. Okay, so we know enough actually about this probability distribution. Remember, we know quite a lot. Just using the arguments of isotropy and homogeneity, we had arrived to the conclusion that okay, the probability to find a particle in the infinitesimal neighborhood of any velocity with components vx, vy, vz, that's what we were asking, needs to factorize. Okay, so it would be the product of three functions, vx, vy, and of bz, and these functions are going to be equal for each component, and this is because of isotropy, and because the probability has to be invariant regardless of which specific system of axes x, y, and z we choose. It cannot depend on the components individually, but rather it has to depend on the modulus of the vector, which is the thing that remains unchanged if I change the reference system. Okay, so this must be the case. So this is what we know about this probability distribution. Okay, so let's now find systematically which function can achieve this. Okay, so it seems a bit difficult that we find such function, or if you already guessed that it's an exponential, well, it is an exponential, but we can actually find that systematically. So let's do it. I will write here just for shorthand v, where v is the modulus of the velocity, and I put this here like that, and make this smaller. So what I'm going to do now is to take the what's called logarithmic derivative. It's only just taking the logarithm of both sides and then taking the derivative of that. Okay, so logarithm of PV, what's the derivative? And we are going to take derivative with respect to any component, say x, y, or z. Okay, let's choose Vx. Okay, what I want is to do the derivative with respect to Vx of the logarithm of this probability distribution, which is a function of p. So what is that? Well, that is 1 over p of b, and the derivative of p of b with respect to v, this is with respect to v, and the derivative of v with respect to vx. Again, that's just by the chain rule, of course. And okay, because v is the, okay, let's just write it here, make a little bit of space just to remember that v is the square root vx squared, vy squared, and vz squared. So the derivative of p with respect to vx is 1 over the square root, which is 1 over v. So let's just write it, pv, derivative, I'm just copying now, pv with respect to dv. And now this would be 1 over v and 2vx, which is the derivative of vx squared. Okay, so that would be it. Fine, and this is just taking the logarithmic derivative of the left hand side of this expression. Now let's take the logarithmic derivative with respect to vx as well to the right hand side. Okay, and what we get then is simply 1 over this little p of bx and the derivative of p, little p, with respect to vx. Okay, so let's just rearrange this. Okay, I'm going to send this to the right hand side. In the end, what I'm left is this calligraphic uppercase p of b, derivative of this p of b with respect to v, and then there is the 1 over v as well. Let me just rearrange it like that. I will put it as a prefactor for convenience. So 1 over v, and then here I write 1 over 2vx of 1 over little p vx, derivative of little p with respect to vx. This is little p of bx, right? Just to make it obvious. So fine, what you see is that the left hand side of this equality is only a function of v. and the right hand side is only a function of bx. Okay, and v is not just fixed by bx, it also depends in by on bz. So we have here two things that are equal all the time, and they have to be equal for any value of b and any value of bx. That can go from minus infinity to plus infinity. So the only way that this can possibly be true is that both the left hand side and the right hand side are equal to a constant. Okay, that's why they agree for any value of the variables, because they're actually a constant. And this constant, let's just write constant. For convenience, I'm going to write it like minus a. Okay, and let me just integrate this expression. Okay, so what I have there is 1 over 2 vx, 1 little p of bx, and the derivative of little p of bx with respect to vx. And this is equal to this constant, I mean, you just integrate, just remember that this thing here is the derivative with respect to vx of the logarithm of little p of bx. And the right hand side then is 2a vx, 2a vx. Integrate that, and what you get is the logarithm of little p vx. If you like, you can put here some constant, right? So logarithm of, that's just the integration constant that I choose to call logarithm of c. And on the right hand side, you get e to the minus a vx squared. Okay. So, sorry, this is not what you get yet. You get minus a vx squared. Okay, and when you exponentiate now, for sure, this p vx, to get rid of the logarithm, is going to be c, some not constant, that multiplies e to the minus a vx squared. Okay, so that's the result. Now we have the explicit functional form of p of bx, but we know that p of bx, p of by, and p of bz, so each of these factors are the same function, so we know the right hand side, and of course then we know the left hand side. We know everything. Now we know what's the form of this probability distribution. Okay, now we have two things that we don't know yet. So we have this constant c here, and we also have this constant a here. So let's try to figure them out. The easiest is the constant c, because remember, we are dealing with a probability distribution, and probability distributions need to be normalized. Okay, so what I know is that if I take this marginal pvx and I integrate over the entire value of allowed velocities, which is just the entire real range, I have to get unity. Okay, so this is c times e to the minus a vx squared, and I have to get 1 out of here. Okay, so this integral is one of these Gaussian integrals that you find tabulated and so on, and the result is square root of pi divided by a. So let's just finish writing it explicitly. So what you get here is c times square root of pi divided by a, which has to be equal to 1, which means c equals a divided by pi square root. Okay, so the distribution looks like this. Now we only have one unknown constant, which is this a. We have to figure it out. So for finding a, we have to resort to what we know about systems, this mechanical systems in thermal equilibrium, that is this equipartition theorem. Okay, so remember that the contribution of the x component to the kinetic energy per molecule, when you average that, what you're having is 1/2 of m vx squared averaged. Okay, and by the equipartition theorem, we know that this thing is going to be equal to 1/2 of kt. Okay, so this is something we established before, and you see that if you calculate the average of bx squared, this is given by 1/2 of kt. And if we have the probability distribution here in terms of a, we go and calculate vx, we will obtain a function of a. Okay, and we know that this thing is equal to 1/2 of kt. So that way we can figure out what A is. Okay, so let's just do that. Fine. So the average of Vx squared is the integral from minus infinity to plus infinity of actually everything. Okay, so that would be Vx, Vy, and Vz. So all of them, these Cartesian coordinates for the velocity. And here you have, well, the product of this Vx, Vy, and Vz. Okay, and the thing that you are averaging is Vx squared. Okay, now because this probability distribution factorizes and we are only integrating this Vx squared, this and that integrate out to 1 because they are both of them individually normalized. And what I get in the end is simply the integral from minus infinity to plus infinity of the marginal Vx, and the integrand is Vx squared, and here you have this square root of a, sorry, like that, square root of a pi, well, let's just write it like this first. Yeah, let's write everything. So this would be the square root of a divided by pi e to the minus a Vx squared. Okay, and if you go and do the whole thing, you find that this gives you 1/2a. Okay, so coming back to this expression above that we had written, we know that 1/2 of the mass times this thing average, which is 1/2a, equals 1/2 of kt. Okay, so this goes with that, and what you find then is that a equals m divided by 2kt. Okay, so finally we have everything we needed, because this probability distribution is now m divided by 2 pi kt e to the minus and then a again, which is the mass divided by 2 kt of Bx squared. Okay, and if you want to write the calligraphic uppercase P, which depends on everything, this would be the product of 3 guys equal to this one. So that would be m divided by 2 pi kt to the 3/2. Okay, and here is e to the minus m divided by 2 kt, and you can write here Vx squared plus By squared plus Bz squared if you like, or you can write V squared if you will. Okay, so this would be the Maxwell-Boltzmann distribution, just the marginal for one component of the velocity, and the Maxwell-Boltzmann distribution for all components. Now, okay, so this is the final result really, right? But there's one important remark that I want to make so that nobody gets confused. You see, these probability distributions are never used on their own. So always when you want to express, remember what is this, right? So I want to express what is the probability that I find a velocity or a particle in my gas, a molecule, that has velocity between v and v plus dv. Okay? And the thing that gives me this object is this uppercase calligraphic PV that I wrote here. Let's just write it explicitly: Vx, Vy, Vz. Okay? Times the element, the differential element in the coordinates where the probability distribution is written. And this probability distribution is written in Cartesian coordinates, even if in the end, it turns out that it depends on v squared. But it's written in Cartesian coordinates, and it makes sense when I multiply by this volume element in the space of velocity. It gives me the probability that I find a velocity in the infinitesimal neighborhood of this v, which is Vx, Vy, Vz. Okay? But imagine that, because everything is isotropic and so on, I prefer to work in spherical coordinates. Okay, integrating out the radial components, because I know that the probability distribution only depends on the modulus of p. Okay, so what I would like is really a different probability distribution. There is a difference. Okay, probability distribution that, yes, it depends on v squared, but it's the one that makes sense when I multiply by the volume element in the spherical coordinates. Remember that dvx, dvy, dvz in Cartesian coordinates translates into, say, v squared, okay, dv, that would be the modulus, times the angular coordinates, that I can integrate them out because of isotropy, so that would be the sine of theta, differential of phi. I take the integral over those angles, and everything gives me 4 pi. Okay, that's just the angular part integrated out. Okay, so if I want to express the probability of finding a particle that has a velocity whose modulus is between v and v dv, which is a different statement from this one, then the probability distribution I have to use is 4 pi, okay, times this m divided by 2 pi kt to the 3/2, okay, v squared e to the minus 1/2 of kt v squared. Okay, so that's what it is. So this is the probability distribution that I would use if the question I'm asking is what is the probability to find particle with such modulus in the velocity, and not a particle in the infinitesimal neighborhood of this specific vx, vy, vz, which is a vector form. Okay, so this is the subtle difference between the two expressions. You have to always be wary of which expression is the one you want to use. Okay, now final comment about this is what we have. Okay, here is some constant, fine, and then here what we have is interesting because it's a comparison of two energy scales. Okay, so if you realize what you have here is the kinetic energy of per molecule, okay, divided by the Boltzmann constant times the temperature. So this is, if you want to think about it, is a comparison of what's the relative weight of two different energy scales. Okay, so one energy scale which is associated with the dynamics of your molecules in the gas, and one energy scale which is associated with the thermal fluctuations at the temperature that you are in equilibrium with. You can imagine that your gas, right, which is at some temperature, that was our initial assumption, is at that temperature because it is somehow embedded in a thermal bath at that temperature. Okay, and the typical energy scale of the thermal interactions between the bath and the system is given by this kT, and the internal energy scale of the system is this kinetic energy. Okay, and the whole probability distribution is determined by this comparison between two energy scales. That's just something to have in mind to interpret this Maxwell-Boltzmann distribution. Okay, so finally this concludes our lecture on kinetic theory of gases, and what we have left now is to introduce statistical mechanics properly. Okay, that would be next week.